we'll start with this one. Number 6, we'll start that as a warm-up. If you graph this, please, on your graphing calculator. Couple of things before we even go to the graph. What are we going to need to do first when we type in our equations? Into the calculator. What are we going to do first? What do you want to change? Okay. What are we going to change off of this equation before we type it in? What are we going to change theta to? We're going to change theta to t first. And what's the other thing that we're going to do? What's the other kicker that we need to be wary of when we're graphing a parametric? Nope. Nope, we're not launching. This isn't a launching type thing. What's the other thing that we need to be wary of? Here, here, and here should tell us what? We have cosine, we have sine, and we have our t values. What does that scream to you? Your calculator needs to be in radians. Okay? So anytime you see a trig function or you see pi, your calculator needs to be in radians for that particular graph. Okay? Graph this one, find me the center. So it should look like this. It is an ellipse. Where is the center of this ellipse? Where would the center of this ellipse be? 1, 2. 1, 2 is up here. That's not even 1, -2. There you go. Yep. Okay. So the center of this ellipse is at 1, -2. Now, based off of my equation, oops, I put -1. Where could have I gotten the center of 1, -2 from without even looking at the graph? From the x and the y. So right here, it gave me a +1 for the x, and it gave me a -2 for the y. Okay? So those two values shift our graph, which then shifts our centers of everything that we need. Okay? That's going to come into play today, because now what we're going to do is, oops, let me get a shade on this one. Okay, now what we're going to do is we're going to graph this one. Without graphing it yet, tell me what shape this is. Why a circle? This one is a circle. This one was an ellipse. Okay. The added values don't have anything to do with anything but the center. This one was a circle. This one was an ellipse. Ellipse. Circle.
Because the values in front are the same?
The values in front. The R values are the same. So that makes this be a circle. What else can you tell me about the circle?
It'll be right in the middle because there's no values afterwards.
So it's got to center it at the origin. Was that yours also?
Yeah, that was
Okay. What else can you tell me about this circle?
The radius is 3.
And a radius of 3. Okay. And we can tell all of that just from the equation. Since the number, the coefficient of the trig functions was the same, it's a circle. It's just an added on one. Okay? Oh, it's number 8.
Is it just this?
It happens.
That's why I'm
No. Okay?
I'm just listening.
So, graph this on your graphing calculator now, please. T values to figure out what happens to our circle. So I'm going to hit tab here, and I'm going to go up to my circle, and I want to play with the t values. So we can go from 0 to right now to 2 pi is where we're at. Let's change those values. What do we want to change those values to be? -5. So that would be on the left. Okay. How about instead of going 4 pi or -5, how about I change this one to 2? Does that work? What happens to my circle? Just gets me a partial one of the circle, yes? Okay. So if I don't go to 2 pi, why is 2 pi so magical? Because it's a full rotation around the unit circle, right? Okay. So 2 pi is magical, full rotation. So if I don't go to at least 6.28, it's not going to go all the way around the circle. Okay. What happens if I go more than 2 pi? Let's say I go to 6 pi. Now what's going to happen? Will I see multiple circles? So what am I going to see then on my graph? Just one circle, but it's going to keep going over itself. It's going to go over itself 3 times. Okay? So I see one complete circle, but if I were to trace this, it would go round and round and round and round. There's up to 6.28, so that's 1. There's 2. And then it would come back here now. If we watch our t values down here in the corner, sorry for people in the back. If we watch our t values now, it's going up to about 6 pi, and then it suddenly jumps back to 0 because it resets itself. Okay? So that's what happens there. Okay? Let's reset that to be, let's reset this to be 2 pi. Okay? So we're resetting that to be 2 pi. So we're back to normal now, back to our original graph. And now let's mess with the t-step. So the t-step right now is 0.13. Okay? If I go to 0.5, I really don't see much. Okay, I don't see much of a difference. Let's go to 1 as our t-step. Okay? So I want to change our t-step to be 1. Did you notice anything about the circle? what do we notice? It's what? It doesn't connect all the way down here for one. What else do we notice about the circle? I don't know if that's a thing. The circle got skinnier. Took some Ozempic.
Yeah.
Okay. Okay. Don't really notice anything yet? Okay. Let's change it to... Let's change it to 2. It makes it what? More rigid. Okay. It makes it less smooth, right? It makes it chunkier. Okay. Okay. All right. Because it's not calculating as often. Okay. So that's why it's doing that. Okay. All right. Love it. So, for any point on the unit circle, what are the coordinates of it? What are the coordinates of any point on the unit circle? Any point. Not a specific one. Any point. X, y could be any point anywhere. I want of what? Cosine of theta or cosine of t? Okay. So for any point on the unit circle, it's cosine of t, sine of t. Which means to graph any circle in parametric form, it would be x of t is equal to r cosine of t, and y of t would be r sine of t. And that works for any circle. Okay? Now, what we just learned a couple of slides ago was if we add something into this box, it moves the center of that circle. So if we add something into that box, it'll move the center of the circle, and it's straight up. So if it's -2, it moves it either down 2 or left 2. If it's plus, it moves it up or left. Excuse me, up or right. Misspoke there for a minute. Okay. With that being said, what is the parametric equations of a circle with radius of 30 centered at the origin? What are the parametric equations for that? No variables? Say louder, Ms. Push. 30 cosine of t. Yep, we gotta have the t. We gotta have a variable in there, yeah? So this would be x of t would be 30 cosine of t. Y of t would be 30 sine of t. Okay. Same circle, but now the center is at the point -5, 18. What is the parametric equations? For x or for y? Okay. Okay. So x of t here would be 30 cosine of t, then -5, and y of t would be 30 sine of t, then plus 18. Same circle, center is now at 0, 25. X of t is 30 cosine of t. Anything added or subtracted? Y of t is 30 cosine of t. 30 sine of t makes a difference. Plus 25. Yep. Okay. All right. Reason that we need to do that is the main focus this week is going to be riding a Ferris wheel. Okay. Is anybody unfamiliar with a Ferris wheel? Okay. Some people are. Has anybody ridden on any cool ones before? Which one's ridden on? Chicago? The one on Navy Pier?
Yes.
Yeah?
Big one.
Big one? Yeah. There's a couple of big ones out there. There's a big one in London. I forget what the name of it is in London. London Eye. Yep. And then there's a big one in Vegas. And then I don't know if there's a semi-big one in Orlando, but it's not as big as the one in Vegas and London Eye. But the coolest one I ever went on was in Cleveland. I know you're shocked to me to say cool and Cleveland in the same sentence. But so they had this exposition center. They called it the X. I know. Real brain surgeons on this one. Okay? And they put in a bunch of like carnival rides and carnival games and all that stuff in there. And you paid one admission fee and you got unlimited rides. Well, in the middle of it, they had this Ferris wheel. And they cut the ceiling out and then put glass up on the ceiling so that it was weatherproofed and that it wasn't, because Cleveland gets cold. And so then you loaded at the bottom, and then you went up, and you could see all this. I mean, it was probably, the exposition center was probably from, I would say at least the baseball diamonds to here. And at least, here to the road wide. I mean, it was this huge exposition center. And there were hundreds of these rides. So you got to see, and this was right smack dab in the middle. And so you got to see all these rides. And then you went out through the ceiling, and then you saw downtown and Lake Erie and all the different parts of Cleveland. And then you came back down and you kept doing it again. So that was pretty cool. It's a cool one. $1 billion idea for anybody. I'm giving it away for free. Okay? All I ask for in return is a lifetime pass. Okay? Unlimited rides. Okay? Instead of going up and through the ceiling, I want a Ferris wheel that goes down into the ground. Okay? So you cut a trench, and then the Ferris wheel goes into the ground. And then on either side of the Ferris wheel, I want an aquarium. Okay? So that when you're at the top of the Ferris wheel, you can look down on the fishies. Okay? And then when you're at the bottom of the Ferris wheel, you can look into the fishies. Okay? And it goes slow so that you can actually enjoy and see stuff when you're going there. The Ferris wheels don't have to go lightning fast. Okay? A nice slow aquarium. So that's my $1 billion idea for anyone. I just want a lifetime pass. Okay? All right? So, we've got a Ferris wheel with a radius of 30 feet, rotating counterclockwise at a rate of 1 revolution every 20 seconds. The bottom of this Ferris wheel is 10 feet off the ground. What position are you 22 seconds into the ride? We're going to need to call upon some first semester math right now. Okay? Back in the day, and I say back in the day meaning back in late first semester, we graphed sines and cosines and tangents and all of the trig functions. Okay? Remember that? Okay? We had, back in the day, we had a function, f of x was equal to a, and then it was sine or cosine of b times x minus c plus d. Remember that formula. A did what? It was the amplitude. A was for amplitude, so the vertical stretch. B was what? Testing some memories here. B was the period. Okay? C was what? Was where we started it, right? Where we started our first lap. And D was... No? Shifted it vertically, right? Okay? Right? So we had all of that. Well, now... Okay? Now, we've got a parametric function, and that parametric function we're going to use to graph Ferris wheels, circular motion, if you will. So now we've got x of t, and that's going to be a cosine of bt plus c, then plus d. Okay. Y of t is going to be a sine of the same thing. Now, we got to figure out what all that stuff means. Okay? Right? So A here is going to be the radius of your circle. Okay? A's positivity is also going to be your direction of travel. If A is positive, you are going to go counterclockwise in your motion. If A is negative, you're going to go clockwise in your motion because that comes out of the unit circle. Okay? Positive angles go counterclockwise on the unit circle. Negative angles go counterclockwise on the unit circle. Okay? So that comes into play. B is going to be the period. Now we've got to remember from back in first semester that 2 pi divided by b was my period. Okay? Or simply that b was equal to 2 pi divided by the period. Either one of those work. Okay? But we got to remember that because we need to find our period. Period, remember, the amount of time it takes to get back to the same spot. Okay? Pound, pound, pound. C is going to be your start, or if you're on a Ferris wheel, it's going to be where you load the gondola. And that's based off of the unit circle. So if you load over here on the right, your C value is 0. If you load at the top, your C value is pi over 2 or negative 3 pi over 2. If you load at the left, your value is plus or minus pi. If you load at the bottom, it's positive 3 pi over 2 or negative pi over 2. Okay? Depending on where you load. Okay? And D, what color didn't I use? Blue. D is going to be the center. So the x part of the center goes for x of t. The y part of the center goes for y of t. Okay? With all of that being said, now we can come up with our Ferris wheel equations, so that we can graph our Ferris wheel equations, and then we can plug in and find the value that we need to find to figure out our position. Okay? So, x of t is going to be a. What's a in this case? What is my a value for this scenario? 30. Is a positive or is a negative? Positive, because we're going counterclockwise, right? Forgot what my color scheme was. Green. So that means positive 30. Okay? So x is going to be positive 30. Y is going to be positive 30. X is going to be cosine. Y is going to be sine. Okay? One revolution every 20 seconds means that that's my period. Period is the amount of time it takes to get back to the same spot. So if you're going around once every 20 seconds, you're getting back to the same spot every 20 seconds. So my period is equal to 2 pi over b, or b is equal to 2 pi over my period. Well, if my period is 20 seconds, then that's 2 pi over 20, which reduces to pi over 10.
If it was like 2 revolutions every 20 seconds, would it be like 10? Like 2 pi over 10?
So it'd be 2 pi over 10 or pi over 5. Yep, and that does come into play. T and T. Where are we loading in this one? Loading at 0, right? Because we're loading on the right side. So that means we're going to load at 0. So we could go plus 0 here if we wanted, but we don't have to, because adding 0 does nothing to it. Okay? Where is the center of my circle? It's at 40, right? 0, 40. So this center point is at the point 0, 40, because this here is 30, and we also told us that we were 10 feet off the ground. So that means that I have to add in to my y value a plus 40. Okay? t range. Obviously, when we start the ride, we're starting at 0. How high do we need to go with our t value? At least 70? Do we agree with at least 70? I'll change my question. What is the smallest value that would give me a complete circle going to be? 2 pi would not get me a complete circle. What do you got? 20, because it takes me 20 seconds to get around. So this number here needs to be at least 20. Okay? I don't care what it is that you put in. It needs to be at least 20. Okay? All right, so let's graph this thing. I'm going to go back here into this one, and I'm just going to clear it all out. Resets it all. So my x of t was, again, 30 cosine of, make a fraction is control divide, pi over 10 t. Y value was 30 sine. If you don't like using the keystroke to find pi, you can always just type in the word pi over 10 t. Then that one had a plus 40 on the end. And we said that we needed this number to be at least 20. I'm going to go 30 with it. When I hit enter, why don't I see my Ferris wheel? We adjust our window. Now, we can mathematically think about what our window is going to be. X values. How far left do we need to go with our x's? We need to go at least negative 30. So let's be able to see it. Let's go negative 40. Which means I should probably go 40 to the right also. And I'm going to go by 10s just because I can. Vertically, do I need to go below the ground? No. I'm going to go negative 10 just so we can see the ground. Maximum, Ms. Bushman, you said how high do we need to get? At least 70. So I'm going to go 80. Again, going to go by 10s. Now, when I graph it, it doesn't look very circular. Okay? And that's because of the aspect ratio of your viewing screen or of the calculator. It's not a perfect, 1-to-1 aspect. So to square that up, we can go menu, window zoom, and then if you scroll down here, it's letter B. You can always just, oops, I didn't want to say H. You can always just say letter B, and it'll square up your window for you. Now, the downfall with that is that you lose that nicitudeness, but you can grab onto one of the axes and bring that back in. And there you go. Now, when we trace, I'm going to trace step by ones, because I don't want to go by tenths. I want to go by full seconds. And now, when I trace this, so there's my position at 0 seconds. We are 30 feet to the right and 40 feet off the ground. Okay? And then each second, After 5 seconds, we should be at the top, 70 feet off the ground. 15 seconds, we're at the bottom. We're 10 feet off the ground, and we're moving in a counterclockwise manner. After 20 seconds, we've gone 1 lap around. So our position after 22 seconds is we are at 24.271 feet to the right of center, and we are 57.634 feet off the ground. Have yourselves a great, grand, and wonderful day.